Okay, so now we're going to be talking about PT phase diagrams. So we'll review a little bit of PV phase diagrams and then show how they're connected to PT phase diagrams. So PT would be pressure temperature phase diagrams. So here's our PV phase diagram that we had last time. Only this time it doesn't just show the liquid area. Like we had the liquid gas equilibrium and then we had the liquid region. But now we have the freezing point or melting point here. And so this is the equilibrium between solid and liquid. So we've added this region, and we've added this region down here, the solid gas equilibrium region. So let's walk through these different lines through this phase diagram. If I drop you in any one of these regions, you can kind of read what's going on. If I drop you right here, you're going to be in the solid state. If I drop you right here, you're going to be in the liquid state. If I drop you right here, you're in the gaseous state. That seems obvious. If you're in this region, what do you have? Well, you've got a liquid with a meniscus and gas above it. So you've got equilibrium in this shaded region. Here, if you're dropped into this region, you have some solid and some liquid. Now, depending upon the densities, the solid might be on top, like in ice. Ice floats above its liquid, but in all the other solids, the solid is below the liquid. The liquid is less dense than the solid. And then down here you have like dry ice and air. So you got dry ice, solid, and then the gaseous CO2. So below this point, you don't have a liquid. You just have solid and gas equilibrium. So we can look at this. Let's say we start out with our piston way down here. Let's do B in this column. So our piston's way down here, and we've got solid. So we're right here at this point. Can I just do one? We'll do one, okay? And so it's all solid. But then when we get to here, it's going to be in equilibrium with here. So we raise the piston up to here, say, and say we're right. Let's say we're right here in the middle. Then we've got a little less solid, about half as much as we had, and then a lot of gas particles. So it's going straight from solid to gas. And you see it's a solid because it's not taking the shape of the container, right? It's just sitting over on the side, okay? Maybe I'll draw some like roughness or something. Okay, so we know that's a solid. As I move the piston up, all I'm doing is moving this fulcrum here to the right. So now I'm right here. And you can treat this fulcrum like a seesaw. Do y'all remember? Have y'all ever played on a seesaw? It's a board, and you seesaw up and down, right? Very dangerous thing that we had when I was a kid. And so if you're going to balance this seesaw, okay, what size are the kids? Okay. So on this end, look, this board is really short on this end. So it's maybe not politically correct, but I'm going to draw a really big chubby kid here. Okay. All right. So he's holding on. And then down here we got this little tiny guy. And he's holding on and he's hoping that that big kid doesn't jump off. Okay. That's one thing we always had to promise when we were doing seesaw. It's like, you want seesaw? Yeah, but no offs. And the guy had to say no offs, and then you could get on. But do you see why that is? So when the fulcrum is here, so this is where we are. So that was one. This was two. This is three now. So we're up here. It's two. This is three. So we're here at three. You see that the gas kid, there's way more gas than there is solid. So the solid will have shrunk quite a bit at 0.3. I know y'all can't really erase, but it's a progression. You can see it on the video. And then when we get to 4, when this fulcrum gets all the way to the right and it's in this blue space, it's all the way up and we have only gas. So this is 4. And the solid is gone. So you see as that piston goes up, the solid sublimes. It's going straight from solid to gas. Why is that? Well, because it's too cold in temperature. It's below the point where there'd be any liquid. Okay. Now, if we raise it up, we could imagine going through this one here at A, we would have, again, 1, maybe here's 2, where we have solid and liquid. 1 is easy. It's just the piston all the way down on the solid. Let's go to 2 here. 2. So we'll do A over here. This is A. Line A. And so 2, we've got some solid. I'll draw it kind of weird so you know it's not liquid. And this is all liquid. So that's where we are at 2. We're at some equilibrium between the solid and the liquid. But when that fulcrum moves all the way over here, and it's in this region, oh, this is 3. Then the solid is gone. It's completely turned into liquid. Does that make sense to everybody? We've expanded the chamber and the solid has all melted. And then we get into the liquid gas region where the liquid starts to show some vapor pressure. So let's put our fulcrum right here for question. No, the isotherms. So like if this was an isotherm of A, it would come out like this, okay, and then it would go up steeply like this, and then it would hit here, and then it would go up steeply, very steeply right here, like that. Yeah, so that would be an isotherm through this drawing. So we are, as we go across, here on a straight line, we are actually raising the temperature. And so that's again why the solid is melting and why the liquid is turning to gas. But if you'll notice here, the solid liquid equilibrium has a straight horizontal line here. That would be that transition between solid and liquid, and that would be at that pressure, the melting point of the solid at that pressure. So melting points are also pressure dependent. Okay, and then we'd have the boiling point of that liquid at that pressure. So whatever pressure this is. The only time we have the normal boiling point is when that vapor pressure is 1 atmosphere. But you have think about Mile High, Denver, right? The boiling point is lower because the external pressure is lower. And so it's a logarithmic relationship. So, the pressure has a decent impact on the temperature. And so at 4, we've now got some liquid and some gas. So we've got liquid. I'll just draw some gas up above here. And then we get to 5 when we're all the way into the gas region here at 5. And then we have gas only. And our liquid phases are completely gone. Everything's boiled away, and the piston's only full of gas. So does everybody understand the horizontal lines through this? We are moving that piston to make the pressure stay constant. So we're having to warm these up because we're crossing several isotherms. And so the pressure would not stay constant if we're warming it up, but we're moving the piston out. And that's why I'm showing this horizontal progression through the volume axis. So we're warming it and we're expanding the volume, so they're keeping the pressure constant. So these are isobars. These A and B are isobars. Okay. Now here, you see the little flame down here. If we keep the volume constant, V, okay, and we add temperature, then the pressure is going to go up. Something's got to give, right? And so this is situation C, where we've got a fixed volume. So we're down here, solid gas at a low temperature. So we've got a solid and we've got some gas. So that's situation 1. Then we get to the triple point. So we've warmed it up, and some of that solid, let me make the solid really super solid, right? So that's our solid. We get to this point. So this is situation 1. Does everybody see situation 1? So down here, 1. We get to the triple line, 2, and we have 3 phases in equilibrium with each other, the triple point. So here now, some of the solid has melted, so I'm going to draw like little waves, right? Like a liquid. Okay, and it's not as dense. But we have some solid, we have some liquid, and we have some gas. Now here we are in at 2, this is our fulcrum. And now this is a very complicated seesaw because we've got 3 kids on the seesaw. Okay, so we have 3 phases in equilibrium. So we got a kid here that may not be quite as plump as the last one. Okay, I'll try, because he's balancing 2 kids. So we got a little kid here and we got a smaller kid here, because it doesn't take much out there on the end to balance with the plump kid. Okay, does that make sense? So those are our 3 phases that are in equilibrium at the triple point. So we should have a real tiny amount of solid. So my solid is really, really too big. So at that point, we have just a tiny amount of solid left, a decent amount of liquid, and mostly gas. The plump kid is the gas. Do these analogies help, or is everybody just so offended they want to leave? Okay, not making any value claims here. I'm just talking about amount of moles. Okay, so then we're in the liquid gas. So all of the solid goes away, and here we are at 3. Okay, and so now the solid is gone. So we're warming it up, and we have liquid and vapor in equilibrium. And then we get to here, and we run out of liquid. So now the liquid is gone, and we have vapor at a higher pressure, right? We've added temperature, and so we just have the gas molecules are just really cruising. They're going fast through here. Yeah. So a high pressure gas all the way up here to C. Yeah. And so we've melted all the solid, we've boiled all the liquid, and we're just heating up a fixed container, and we have a gas at higher and higher pressure. And we should stop eventually, because you don't want to heat a closed container, because it'll blow up. Okay. So are you comfortable with the C line? Which one of these 3 are you most comfortable with? B is probably the easiest. You're just going straight from solid to gas. Now we will do some math on this lever rule. Eventually we'll do it when we do two layer liquids. So we'll track the number of moles in each layer of the liquid and so on. So we'll actually get into the seesaw equation, the lever rule equation. But it's one of these situations. Anytime you have 2 phases in equilibrium, you use what's called the lever rule. You have the fulcrum, and you have the lengths to either end. And the number of moles is proportional to the lengths of those distances. Okay. Let's take what we just drew, these A, B, and C lines, and put them on a pressure temperature phase diagram. Does anybody ever remember seeing this kind of phase diagram? Where did you see it? Freshman chem? Yeah. Yeah. So this is one of the ones they teach in freshman chemistry, because you have melting points and you have boiling points, and you can see them right there on the graph. So here we have 1 atmosphere right here, and so where that intersects this solid liquid interface, these lines are the equilibria, and so there's your melting point, here's your boiling point. TB is T boiling, TM is melting. Okay. Now always, whenever you're starting any kind of these phase diagrams, you get a graph on the exam or you pull up one in the book or the internet, always go to the axes first to see what you're dealing with. So you look at the vertical axis, you got pressure. You look at the horizontal axis, you got temperature. And now you got to figure out where the regions are. So how do you know it goes solid, liquid, gas without just remembering solid, liquid, gas? I mean, think of this. This is low temperature, high pressure. Low temperature is going to be solid. And solids, high pressure works as well too. Over here, you've got high temperature, low pressure. So that's a gas. High temp, low pressure. And then in between would be the liquid phase. So that's how you can logically think your way through it. These lines are all of the equilibrium lines. So down below this triple point, that's that sublimation point where you're going from solid straight to gas. And then here you go from solid to liquid, that's melting equilibrium. And then here you go from liquid to gas, that's the boiling or vapor pressure equilibrium curve. And you see that curve is logarithmic or exponential. It's that change in pressure with respect to temperature goes up. If we were to take the natural log of that pressure and 1 over temperature, we'd get that vapor pressure curve, the linear one, with the slope being the delta H of vaporization. So we just narrated A. We went from solid, we hit that point where we had solid and liquid phases in equilibrium here. And we can't see the two phases in equilibrium like we can in the PV. The reason we can see them in the PV is because they have different densities. So they have different volumes. So we can't see the density on this chart. We can see the density on the PV chart. So the different phases have different volumes per mole. And so that's why we have that region that's kind of split with two volumes. And there's really nothing in between. The thing in between these is just the fulcrum. There is nothing here. It's either there or there, and it's a seesaw between how much you have. So I can put the fulcrum here, but when I put the fulcrum here, it's a seesaw between the two phases. And one phase decreases and the other increases as the fulcrum moves. So if I move it this way, I'm producing more solid. If I move it this way, I'm producing more gas. And what moves it is temperature. Well, on the temperature, that's what we have in PT. I'm going along, I hit this point, let's do one more. I hit this point and it stops. And right there, that fulcrum is moving from the solid phase to the liquid phase. So it's kind of coming out at us until it hits the liquid volume. And then it starts moving again. And then it hits the boiling point and it stops on the temperature curve. But it starts moving on the volume axis across. That fulcrum moves until it hit the volume of that gas at that temperature, and then it starts moving into the gas region. So these two charts are related to each other. We could do the one for sublimation. This was B. We're coming along. We're warming up the solid. We hit this point, and then that fulcrum is moving from the volume of a solid, the density, which is number of moles of solid, gives a certain volume. And we move those same number of moles, gives a certain volume of the gas. And then we move across, and we're warming up the gas. Yes?
Like a on water and covered it with like a good layer of oil. And heated it.
Oil. Mm-hmm.
What with the water and the boil since there's no vapor, like
It's under 1 atmosphere pressure from the outside. So that atmosphere pressure is pushing on both of those layers, and the water would boil at its boiling temperature. Let's say there was no oil mixed into the water, so we didn't have boiling point elevation. We just had the boiling point of water. It would boil, and those cavities would make their way up through the oil and burst at the top. It wouldn't stop the vapor to leave. Yeah.
but I guess my question is how does the vapor pressure of water what would the vapor pressure equals atmospheric pressure?
Yeah, yeah.
So if there's like a layer of oil on top
Barrier, yeah. If you were to, have the piston, right, and measure, the water would make its way through the oil and into the vapor phase. So it would push that piston up. You would measure the pressure. The pressure increase would be from the water because the oil would have a very low vapor pressure. Yeah, so You would be able to measure it. It might be slower to develop and react to temperature. Um, Now, they do put oil or they put polymers and things on top of water to reduce um, the evaporation rate. Okay, and so that I think that's just reducing the surface area exposed to the atmosphere to slow down the equilibrium. So it's just not able to develop the equilibrium vapor pressure as fast. Okay. And if you're like in a reservoir or whatever, they have these covers that they put out, these plastic beads and so on to kind of keep in the daytime when this reservoir is, the sun's beating down on it, they don't want a lot of water to evaporate. So they try to hold it and keep it from trying to achieve equilibrium. So it's really a kinetic effect that they're doing. They're not actually going to be able to hold that water in place, but maybe they can hold it in place during the day, and then at nighttime it cools back down. Yeah. And so then this last path that we had, this a C path that goes straight up where we just heat things up, but we stay kind of within equilibrium, is this one. So it starts out down here and it stays in the solid sublimation equilibrium and goes through the triple point. That's where we had 3 kids on the seesaw. Then we're in the liquid vapor equilibrium, but then eventually it leaves that liquid vapor equilibrium and goes right into the gas. So this dotted line is the path of C on the previous chart. So if you want to compare those in your notes, you can see all 3 of those paths here on the PT diagram. And then D is kind of interesting. This is, let's see, this is for water. Yeah, so this is a kind of a weird one. So we're coming along and we have the solid and we release the pressure and it becomes a liquid. So we're coming down, we're reducing the pressure of the solid and it becomes a liquid. That's typical that the liquid is less dense than the solid, so it is able to expand and take up less room than the solid. In water, that solid liquid line is cocked backwards and it has a negative slope, and so we'll see some ramifications of that. Now, in talking about phase diagrams, we have this thing called the phase rule. Like how many phases can intersect? We've got an example of 3 phases intersecting. But this phase rule shows us that 4 phases intersecting is not possible. So I'm just going to go through this quickly because I want to move on to something else. So this phase rule is the number of intensive variables like pressure, volume, temperature that can be changed independently without disturbing the number of phases in equilibrium. C is the number of components in a system. So a pure substance has C equals 1. And then P is the number of phases in equilibrium. So let's look at an example here. So here's phase alpha, beta, gamma, epsilon, delta, and so the phase rule shows that this point right here is forbidden for a single component. It's not forbidden for multiple components, but for a single component it is forbidden. And so what this would tell us is we're trying to map out a phase diagram and our data points are going along for all these equilibrium lines. And it looks like all 4 of these data trends are going to intersect in a single point. We know from the phase rule that it's not. So what's going to happen is one of these lines, it's like a game of chicken. One of these lines is going to divert. And so let's say it's this one and it diverts at the last second and goes over here. So we have this line that goes like this. And so we have a triple point here and a triple point there. So this line isn't there. And this is just how the phase rule has helped us sort of map out some of these phase diagrams. That's as deep as I want to go with that. Oh yeah, let's talk about that. Okay, so here's the phase diagram for water, which we're familiar with, ice and liquid water and steam. But look at the pressure over here. This is the region that we deal with. 1 atmosphere, maybe a little bit higher pressure, certainly lower pressure than 1 atmosphere. We're familiar with that. But when we get up, look at this break in this line here. Now we're talking about 2,000 atmospheres, 4,000 atmospheres. And we have all these different phases of ice. Yeah, so think of different crystal structures. Remember your oxygen dimer, and you know the Excel labs are there to really teach you the science behind it. It's not just because we don't have enough lab space. We have plenty of lab space. We could do lab things, but that oxygen dimer, we had all those different phases. We had the lowest energy one, the tetrahedron, which took up the least amount of volume. We had the square planar. We had the rhombus, T-shape. We had all linear. We had all these different ways to put those atoms together, and that's what's going on here with these different solid phases. So we have different phases of ice and the way it can fit into a crystal structure. And so some of those take up less volume, but you know, ice may not necessarily want to be in that tight of volume. Maybe it wants to expand. Well, if we're at 8,000 atmospheres, it can't. So it's going to adopt the smallest volume it can. It's uncomfortable, okay, but it's going to do that. If we release that pressure a little bit, we get to 6,000, it's going to shift to another crystal structure, ice 5. Now this is kind of an interesting one. Notice that we have ice 1, ice 2, ice 3, ice 5, and ice 6. What do you notice? Let's count. We have ice 1, ice 2, ice 3, ice 5, and there's no ice 4. What happened? Well, they had experimental evidence for what they thought was ice 4, and then later on, as they looked deeper into it, they realized ice 4 was really ice 3, or ice 5. I can't remember which it was, but they're like, nope, we've already started labeling ice 5 as ice 5, and ice 6 as ice 6, and ice 4 really isn't its own unique phase. We're not going to change the labeling of those. We're just going to get rid of ice 4. So that's why science is messy. In the literature, we want to be consistent. So we don't want to have to retroactively change the other ice 5 and ice 6 data. And so we just pushed ice 4, out. Sorry, it's like Pluto, So notice water too, this negative slope to the ice liquid line. And so that means that as we go up in pressure, one way for that system to relieve that pressure is to get into a smaller package, and a smaller, more dense package is liquid. So liquid water is more dense than ice, and this is unique to water. There may be other substances that have that, but I don't know of any. And this is really fantastic. So if ice didn't float, I mean, we wouldn't have any fish. Certainly in the freshwater things where it would freeze from the bottom up, And so there's lots of things, lots of ramifications. If ice didn't expand when it froze, we wouldn't have soil, we wouldn't have agriculture, we would not be alive. This is one sort of trick of nature that allows life to exist. So water is a really unique substance. Here's the experimental phase diagram for CO2. We've already talked about the critical points for CO2. You can see that here. 304 degrees, 72 atmospheres, and up here is that supercritical region, SC. Here's the experimental phase diagram for helium, and this is kind of nice because it shows the two crystal structures for helium, body-centered cubic and hexagonal close pack, which is also face-centered cubic, FCC. And so you can see there the distinct crystal structures that you would have for the two solid phases for helium. This also talks about two liquids. So there's helium-1, liquid helium-1, and then liquid helium state 2 is a superfluid. That's a fluid that has no surface tension. So there's no energy penalty for creating surface, whereas most substances have a preference for being in the liquid state and not on the surface state, so down in the bulk. And then you have the gas. So this is the most glorious slide in all of thermodynamics. okay? Because we spent all morning talking about PV diagram, and then I tried to get you to understand how PT diagram was PV related, and this is it. That's the 3D, the combination of PV and PT. Isn't that cool? When I saw this diagram in one of the textbooks, I got so excited. I went out and 3D printed it. So there you go. There's that. And this is, that's just around. So you can look at it and see the PT diagram, pressure, temperature. And then you can turn it this way and see the PV diagram. And you see it if you look at the PT plane. So here's the PT plane. You see the solid vapor equilibrium line, triple point, and the solid liquid, and then here's the solid liquid. And, no, this is liquid gas. So now this one has a little lip on it like that, and that's because water, the solid is the volume. The solid is got a larger volume than the liquid. Most of these would go the other way, but since water has a solid has a larger volume than the liquid, it has like a little shelf in the inside. So that's a little bit. And then here's the Carnot cycle out here, right? So you can see the steepest descent for the adiabats, and you see the isotherms kind of don't go down the steepest part. They go, because this is the temperature axis, so an isotherm is just a straight line next way. And an adiabat is more straight down the hill. So it's great stuff. And then, again, you should be able to walk through any of these paths. A is solid, B is the beginning of melting, right? And then it melts, and then you have liquid. From C to D is liquid, and then you have boiling, liquid to D to E equilibrium, and then E is just the hot gas. A critical point is going to be up here, the critical, supercritical fluids. And there's our Carnot cycle. So that's great stuff. The rest is just talking about it some more. I think that we're out of time, but I think that's a good run.